Space exploration is entering a new era, driven by both the ambition to reach farther and the challenges that come with venturing beyond the familiar boundaries of our solar system. Let's delve into three of the most pressing and fascinating topics shaping the future of space travel: the formidable hazard of interstellar dust, the transformative potential of nuclear reactors on the moon, and the exceptional promise of Lagrange points, especially the L2 point, for science and settlement. First, consider the question of interstellar travel. Human curiosity and technological progress have fueled dreams of sending spacecraft to distant stars. The concept of interstellar travel, journeying beyond our solar system to neighboring stars, has transformed from science fiction to a tantalizing possibility. Yet this vision collides with a reality that is both invisible and deadly: interstellar dust. At the scale of the cosmos, space is not truly empty. Between stars lies a sparse sea of gas and dust, with particles ranging from mere molecules to tiny grains barely a fraction of a millimeter across. While these particles pose little threat to slow-moving objects, the calculus changes dramatically at the extreme speeds required for interstellar travel. Imagine a spacecraft hurtling through interstellar space at 50% the speed of light, an astonishing velocity necessary to reach even the closest star systems within a human lifetime. At such speeds, a dust grain's kinetic energy is magnified to catastrophic levels. What would be a harmless collision at low velocities becomes an explosive impact, capable of punching holes through even the most robust spacecraft hulls. Recent studies underscore the severity of this risk. Even microscopic grains, when encountered at relativistic speeds, can deliver enough force to vaporize sections of a spacecraft or compromise critical systems. The challenge is not merely theoretical. Concepts like breakthrough starshot, which aims to send tiny probes to Alpha Centauri at a fraction of light speed, have faced scrutiny over this very issue. Shielding a craft against interstellar dust requires innovative solutions, from advanced composite materials to electromagnetic fields designed to deflect or absorb incoming particles. The problem is compounded by our limited knowledge of the distribution and density of interstellar dust. While the solar system's environment is relatively well mapped, the interstellar medium varies in ways that are still being unraveled. The risks aren't uniform. Some regions are dustier than others, and certain trajectories could be significantly more hazardous. Therefore, successful interstellar missions will demand not only revolutionary propulsion systems, but also real-time monitoring and adaptive shielding that can respond to unexpected threats. The quest to solve the dust dilemma is ongoing, and its resolution will be pivotal to humanity's ability to reach new stars. Turning our gaze closer to home, the moon has re-emerged as a focal point for human spaceflight. The vision of lunar bases and sustained operations on the lunar surface is no longer a distant dream. However, the moon presents its own suite of challenges, chief among them, the need for reliable energy. Unlike Earth, the moon experiences day and night cycles that last about 14 Earth days each. During the lunar night, solar panels become useless, and the temperature plummets. For habitats, scientific experiments, and resource extraction to continue uninterrupted, a consistent power supply is essential. Enter nuclear reactors. Recent discussions have emphasized the critical role of nuclear power in enabling long-term lunar habitation. Nuclear reactors are not dependent on sunlight and can deliver the steady output needed for life support, manufacturing, and communications. Unlike solar panels, which are vulnerable to dust accumulation and long periods of darkness, nuclear systems can operate continuously, providing heat, electricity, and even the potential to produce fuel through in-situ resource utilization. The technology is already under development, with major aerospace companies and government agencies collaborating on compact, robust reactor designs specifically engineered for space environments. The importance of nuclear power extends beyond the moon, too. On Mars, for example, dust storms can blanket the planet for weeks or months, rendering solar panels ineffective. The versatility and reliability of nuclear reactors make them indispensable for the future of off-world bases. Beyond technical feasibility, There are also regulatory and environmental considerations, but the consensus is building. Nuclear energy is likely to be the backbone of sustainable extraterrestrial infrastructure. Now let's shift to the marvels of orbital mechanics, the Lagrange points. These are the 5 positions in space where the gravitational forces of 2 large bodies, such as Earth and the Moon, or Earth and the Sun, create regions of equilibrium. Of special interest is the Earth-Moon L2 point, located beyond the far side of the Moon. This is my favorite Lagrange point, and for good reason. The L2 point offers a stable location with minimal gravitational disturbance, making it an ideal spot for scientific observatories, communication hubs, and even future habitats. The significance of L2 has only grown in recent years. Space telescopes stationed there benefit from an unobstructed, continuous view of deep space, shielded from the thermal and electromagnetic noise of Earth. This is why missions like the James Webb Space Telescope were designed to operate from an L2 orbit. The location enables prolonged, uninterrupted observations of the cosmos, opening new windows into the early universe, exoplanetary systems, and cosmic phenomena. But the utility of Lagrange points extends beyond astronomy. Recent research has explored the dynamics of mass transfer through L2 in binary star systems, deepening our understanding of gravitational interactions. The stability and accessibility of these regions make them prime candidates for future space infrastructure. Imagine a network of supply depots, refueling stations, or even habitats positioned at Lagrange points, facilitating travel between Earth, the Moon, and beyond. Establishing a presence at L2 and other Lagrange points could revolutionize the logistics of space exploration. These gravitationally balanced locations require less energy to maintain a spacecraft's position, reducing operational costs and increasing safety. As humanity contemplates missions to asteroids, Mars, and eventually interstellar destinations, Lagrange points will become essential way stations, nodes in a new architecture for deep space travel. In summary, the path to the stars is both exhilarating and fraught with challenges. Interstellar dust stands as a formidable barrier, demanding breakthroughs in shielding and real-time monitoring. On the Moon and Mars, nuclear reactors promise to unlock sustained activity, overcoming the limitations of solar power. And in the realm of orbital mechanics, Lagrange points, especially L2, offer strategic advantages for science, communication, and future settlement. Each of these topics embodies the spirit of exploration, confronting the unknown, overcoming adversity, and harnessing ingenuity to extend the reach of human civilization. As we stand on the cusp of a new age in space, the solutions we develop today will shape not only how far we go, but how well we thrive beyond Earth. The voyage ahead is challenging, but the rewards, scientific discovery, technological advancement, and a permanent foothold among the stars, are within our grasp. This is the future of space exploration, bold, relentless, and filled with possibility.